Hi, we are again in the German Lutheran Trinity Church, which we renovated over the last few months. It's finalized now. We got a lot of very positive comments, how neutral the smell is, how nice the climate is, and of course how warm the walls are. And today I would like to talk about why we have this effect. Why is it that this wall is much warmer than it was before at the same outside temperature? Why is it, we have this nice example here, a stainless steel plate with two different coatings. Why is one much warmer than the other? I need to talk a bit about water. Water has a high heat capacity and high heat conductivity. That's why we use it to cool engines, to get heat away from the engine, and we use it in hydronic heating, to get heat from the boiler to the radiator in your living room in a most effective way. Insulation should do the opposite, keep heat away. The way it does that is it's typically a low density product with a low heat capacity and low heat conductivity. So it means it just slows down the process of getting the heat, say from this room, into the wall and to the outside. And the heat capacity stores the energy and creates a time lag. The time lag is a bit tricky. On one side we want that. We don't want a house to warm up quickly. That's why we use, for example, mud brick homes with a massive time lag. However, the problem is if a room is hot, it stays hot. That's what we often don't want. Water has a massive impact on how we feel temperature, if we are comfortable or not. Think about 10 degrees on a Melbourne winter day. It feels miserable, it feels cold. However, if you're, say, in the Swiss Alps, minus 10 degrees, dry air, you feel very good. 30 degrees on a Melbourne summer day, quite nice, because it's relatively dry. However, 30 degrees in Darwin is not very comfortable. Why is that? Air at room temperature can hold about 20 grams of water per cubic meter. We feel comfortable at around 50 to 60% relative humidity. So that means about 12 grams per cubic meter. However, at lower temperature, air can't hold that amount of water. So water condenses at a colder wall, and there will be a layer of water molecules. Also, we don't feel as comfortable in general because the relative humidity will be closer to 100%. That's what the human body doesn't really like. We feel uncomfortable. So with that water layer, a very thin layer, what happens? We radiate as people, our heaters, lamps, everything radiates infrared heat waves. Water absorbs these heat waves. And water is a very good heat conductor. So I'm going to do a short drawing. Yes. Here we have our wall, and through condensation we have a few water molecules sitting on the surface of the wall. Now, heat radiation from whatever sources, people in the room, a heater, light, will heat up the water molecules. They absorb very strongly infrared heat radiation, and because also water is a good conductor, this heat will be absorbed into the wall. So the heat energy is actually being taken out of the room and it feels much colder. So how do we actually repel moisture from the surface of the wall? This is our wall. We apply our double hybrid membrane, a dashed line because it's not a solid membrane, it's semi-permeable. Molecules actually can travel through that membrane. It's not sealed off like with a traditional paint. A water molecule in the room or trapped in the wall will, when traveling in the direction of our membranes, will be repelled because it's much less resistance to go to the open space than traveling through the membrane to a denser space. The same thing for water molecules already trapped. They find a path through the membrane to the open space instead of traveling further into the wall. We also have the infrared radiation, which is being reflected, and by that taking heated up water molecules back to the room. Here we can see the arrangement of the inner test unit. 4 distinct chambers labeled A to D. A contains the heatsink. Between B and C are the test samples installed, and D contains the heat element. Next picture shows the test samples. All the heat flow has to go through them to measure their effectiveness effectively. Next picture shows the arrangement of the temperature sensors measuring the temperature in each chamber so we can determine the heat flow. Next picture shows the wired up inner test unit, which is then, what we see in the next picture, placed into an outer box, shielding it from any fluctuations from room temperature or convections, movements in the air. Final picture shows the test arrangement, the outer test box, measurement equipment, and the data recording PC. To make sure we have a long enough test cycle, but also avoiding linearities, we measured over a period of approximately 2.5 minutes, which gave us very consistent and comparable results.